Okay, so far in the tutorial for probability, the green is what we did already. The red is the questions that Miss doesn't really go through at all. I mean, no, if Miss don't go through a question in class, she gonna bring that most likely. So the red are the ones that have the least probability are coming. In the Fourier drive, I have the solutions to those. So if you have the drive, you're just going into probability and you click the first document and you'll see the solutions to all the questions in this tutorial here. So you actually have the solutions. But for those that don't have it, let me know. I'll just send the drive back in the chat. So y'all can click it and go through it. So we started probability last week, which is just the normal laws, independent, conditional probabilities. I'll show you how to implement a tree diagram for the probabilities. So we did all those questions. We did the connected flights question, which is the binary communication channel questions. Make sure you know how to do this one. Question 4, which is the connected, which is two binary communication channels, one after the other. So kind of daisy chain it together. Make sure you know how to do both of them. Alright, 5 to 7. I've never seen that on midterm, never see it in our finals. If Miss do it, good, she does really scratch over that. Alright, so I would like to spend time on stuff that I've never seen her bring. Cause to me it'll be like wasting time. Right? But the big questions, because even if you bring this, it not really testing anything large in probability. So she will, if she bring this, you're gonna be like for 3 5 marks. Right? It's because now a question that she can extract a lot out of you. You can literally just memorize the solution to these things. So that is why I put it in it. We did the green last week. That was the last question I did last week. And then 9 is the same thing, 10 is the same thing. Okay, you just memorize the answer for that. Don't really have much thinking. But as I said, the solutions are in the drive, and if you want to go through together was message me. And then, right, I shouldn't green this out. But that's what you want to do today. Blue, question 13. Um, uh, yeah, this is probably the same one as I read. Okay, because just memorize the answers for these. She tend not to bring questions where you can just memorize something because to her it's just wasting time, right? So 13 and 14. Alright. So and then 15 straight down to 22 is the big boy question. Those are the questions that she does like to bring, especially 21 and 22 as I put it in purple. So for this class, I want to try to do from 15 to 20, which is special distributions. And I want to go through 11 and 12 and get out of the way. And then anything after that is just a practice, grind it out, make sure we understand it, and go back to the probability method. So before I start, anyone have any questions to ask me before I start? Alright, no questions. I look to start the push. So I'm gonna kind of break it a lot. I skip only the kind of theory that Mrs. Luchu. I show you how it does think about the questions. But if you know how to think about the question, you know how to do the question. If you know how to do the question, you get the marks. Right? The proofs helps, but to me that's kind of confusing because I just never know when to use it. But if I know how to think, it'll make sense when to use it. Alright, so a random variable is just anything that can happen, but is not predictable, random. Right? If it's predictable, it will be random. So like what they call it a random. And a variable could be literally anything. That's why it's a variable, right? So there are two types of random variables. So you have discrete and you have continuous. So a simple example of discrete and continuous RVs, which is random variables, is if somebody asks you the size of your foot, or their height. It will tell them 11.56. The values it takes could be in a range, it could be in between values. So simple. So somebody asks you where's your height, somebody might say 5.66 meters. I know nobody does say meters, but it's an example. 4.2 meters. It could be anything in between. It continues. It always changes. It's not fixed values. Right? It could be literally anything. It continues. Another example of this is time. Like if somebody asks you what time it is, it always changes. It's not a fixed time all the time. Alright? So time continuous, height continuous, your length of your foot continuous, your intelligence continuous, it always changing. All those things are continuous random variables. Discrete random variables are the easiest ones because these are the ones that could take fixed value. So if somebody asks you how much marbles you have, you tell them 10 marbles, 3 marbles, 5 marbles, no marbles. Discrete. If somebody asks you how much calculators you have, you tell them 1, 2. How much children you have? Nobody can say, well, I have 2.5 children. No, it's either you have no child or a child. It cannot exist in between numbers. Alright, so those are examples of discrete random variables. Alright, so anytime you're doing these things and you do that question, what I like to do is just ask yourself the question. So if somebody was to ask me how tall I was, obviously I could tell them anything. It doesn't have anything that I cannot see. Say 10.3, 3.2, all those things continuous. So that will be a continuous random variable. But if somebody was to ask me how many pencils I have in my pencil case, I can't have half a pencil. So I'll say 5, 6, 2, 3, fixed whole numbers. There's fixed numbers, discrete. Right? So when you're thinking about it, you could think about it like that. But the stress on it, you don't stress too much. Right? So with discrete, which actually for both of them, the two things that Miss will want you to get is the PDF, which is the probability density function. I'm not really feeling like writing out all these words. Density function. And then the other one is the CDF, which is the cumulative density function. Right, and it's the same thing for continuous. Right? I believe for continuous is PMF, probability mass function, but for now, the formalities don't really need it. You need to understand it. You could always change up the notation after. So you need to know how to find the PDF and the CDF for both a discrete and a continuous random variable. Alright, and from both of these, linking these two, you need to find the expectation, which is like the mean, or mu if you want to call it. And the last thing that she will ask you to get is something called the variance. Alright, so everything on this map, so these here, you need to know how to do it for discrete and continuous random variables. And these two here, you need to know how to do it for discrete and continuous random variables. So that's why I just think to cover the topics that she could bring. So she could bring a data set. No, I should just tell you if it's discrete or continuous. So as I said, the blue part kind of redundant because she will most likely tell you what it is unless she bring it in a word problem. But if she bring it in a word problem, that means she most likely talking about a distribution or a special distribution. So the probability of her trying to mix or trick you up in terms of discrete or continuous, slim. Okay? So there's your checklist. You need to know how to do everything. Expectation, variance, PDF, CDF. Right? So there are equations for them, but as I said, I ain't going through this session to do a set of theory or doing questions, but there's your thought process. Discrete, continuous, PDF, CDF, expectation, variance, and that is your foundation. So we'll have to store here. Okay, so I'll start with the hardest one, the continuous. A lot of people has struggle with continuous random variables. So for continuous random variable, no, as I said, this is a tutorial question, so she will not be telling if it continues. So you don't have to think about it too much. So the first question, they said, find the corresponding CDF, which is denoted capital F of x, and the common f of x is the PDF. So the common is PDF and the capital is CDF, right? So I'll do the question, and by the time I'm doing the question, I'll give you the theory that is needed to do the question. So that means just doing the theory and then wasting time doing that and have less time actually doing the question. Okay, let's do both. So you can actually see how to think about the question. So they gave it in a piecewise function and they gave you intervals. So we have to remember about a continuous data set. Because it's continuous in between different ranges, it might have a different relationship. So between 0 and 1, it might be this. Between 2 and 3, it might be this. Between 5 and 6, it might be that. And not, how to say, for discrete, when you're doing it, as you'll see, you have dashes, or you can say spikes, and anything in between here is 0. Have nothing existing in between. But for continuous, it has a value for every single possible x value. Yeah, it's literally different from discrete. So you have to remember that have a value for every single x value in every one. Okay, continuous. While for discrete, it have to be between fixed points. So let you say 1, 2, and 3, you have a probability. Between 2 at 2.5, you have nothing, because it's a discrete. But for continuous, you'll have a value for it. So you have to remember that. So let me go through. So the first thing we want us to find is something called the CDF, which is the cumulative density function, right? So what that means, and I can write is the capital F of x is equal to the probability of x being less than or equal to x. This is what the CDF is by definition. It's just the probability that x is less than or equal to some value, right? It's just everything at or before it. That's what it is. So as you move forward, the probability that something behind you will tend to increase. So that's how I just think about it. So the first thing you do when you're trying to get the CDF for a continuous random variable, so you draw a line, just draw a random line, a straight line. Pow. Then you know you're going to start with minus infinity and you're going to go up to positive infinity. And what you're going to do now, we're going to sketch the piecewise that they give you here into this line. Alright, so the first interval is 0. So at 0, then the other one is 1, then the other one is 2, and then 0 otherwise. Well, that's what I said. So that's why you're working with. So now you're going to put in the probabilities in between whatever they give. So in this case, between 0 and 1 is at 2. Between 1 and 2 is 2 thirds. And 2 to infinity is 0. And between 0 and infinity, sorry, minus infinity is 0. So this is what you're working with on a line. So the cool thing about this line, remember, it's continuous. So it has values between 0 and 1. For every point in between 0 and 1, you have a value for it because it's continuous. So x could be anywhere in between here, or it could be anywhere here, well, or it could be anywhere here. From minus infinity to positive infinity, the x could be anywhere. So that's all I wanted way to think about it, right? So you are this thick man here. Alright, this is you here. However, tall, short, however you want to be. So you here. Now what you're gonna do, you're gonna start here and you're going to walk in this direction. So you're just walking. And what you're doing, you're kind of looking behind you. So you're going to continue to walk. You're going to walk, keep on walking, just keep walking. And if you were to stop here, for example, you will want to know the probability of everything before you. So logically, if you're trying to add up with respect to the intervals, it will be 0, because between minus infinity and 0 is 0. And then it will be from 0 to this x value that you have here, right? But the problem is you don't know what this area is. So then I will tell you the other concept. Because it's a continuous random variable, the probability is the area under the graph. Yeah, so if you wanted to get the area or the probability from 0 to this x value, which is Stickman stop at, you literally just integrate the graph in between the bounds. So in this case, you're just integrating 1/3 between 0 to x, whatever x value it may be, in between this bound here, right? And let me go again. So I'm just grinding this up. So let me say the Stickman continue to walk, and he stop here. He stop here, right? So now he wants to know what is the probability of everything before him. So here now, remember he start from minus infinity. So all you're gonna do is just add up the areas before him. So he start from minus infinity, so minus infinity to 0 is 0. Plus 0 to 1, it passed this already, so you know it's gonna cover the whole thing. So it'll just be 1, 2. Right? And then plus he in between here, so it's between 1 and 2. Yeah? So to get the probability of, sorry, from 1 to this x in between this bound here, you just integrate the graph, which should be integrated in 2/3. So you integrate from 1 in this case, up to x, wherever x is in between these bounds, and you integrate 2/3 with respect to x. Now when you do all this, you will get the probability or the CDF of everything less than or equal to this arbitrary x value here. So this x value might be 1.5, 1.6, 1.24, 1.3333. It don't matter, but you could get the CDF of it. Remember, you're just cumulatively adding up the probabilities or the areas before it. Yeah? But remember, for continuous, the probability is the area under the graph, which means you have to integrate. Or if it's geometric, it's half base by height, length by breadth, all those things still applies, right? So this line method, I don't always do this. Anytime this one to do a CDF, I will pull up this. I can clearly see what I could carve out and I can clearly see what I integrated. It just make everything right in front of your face. So if Miss was to give you a question, very simple, where you could practically use this. So let me clear up the scribbles I drew. So very simple, let you say, Miss, say, what is the probability that x, don't say that, don't say f at 2.4. Something like that. So you know capital, this means the probability that x is less than or equal to 2.4. So I will do, I already have this drop. I go drop my stick down. So 2.4 is obviously after 2. So it might be like somewhere right here. So there's my stick man right here. 2.4. And I will just look at everything before and I can clearly see everything in front of my face. So if I start from minus infinity, I started at up areas one time. So the first area add up 0 plus a third plus 2/3. And now between 2 and 2.4, that any region where they said the probability is 0. So it would be plus 0 because if I integrate 0 between 2 and 2.4, you just gonna get back 0 practically. Yeah, come on, be integrating between 2 and 2.4 are the equation in between these two, which is 0. So it would be 0 added. And when you add all, I get 1, which makes sense. Yeah, so this here, I love it. I like to use it for CDFs, and you could also use it to get the equations to plot the CDF, which I'm gonna do now. Right, but this here, real cool. You could use it for any CDF question for continuous. It wouldn't make sense using it for discrete because it doesn't exist in between bounds for discrete. It's either 0, 1, 2, or nothing. Okay, so let's look to plot the CDF of it. So let's go use the same graph I have here and run through. So you can actually see how it does work. So when I say plot the CDF of a graph, right, she wants us to integrate. And he just basically doing the capital alphabet, the cumulative density thing. That's basically what you're trying to do. But using that, you can get the equations, which you can just plot afterwards. If you wanted to plot the PDF, simple, pow, pow, x-axis, y-axis. So you have f of x right? So we have 0. And the set between 0 and 1 is a 2. So let's plug a 2. And then from 1 to 2 is 2 2's. And then this is 0 otherwise. Okay, let's do what I tell you. Remember the common one means PDF. And that's it. That's the common one. So now basically they want you to get the CDF, which is the capital F of x. Right, so that we'll be using this line method that we have here. So let's go and erase this for now. That's kind of one space. I mean, I have space, but I don't want to screw too much. So let's go. So the first range that you have to get for the CDF, remember a CDF will start from 0 and it can go to 1 and then 2 and then we don't care about anything after that because we have nothing after that. So you have to get different ranges. And remember for the CDF, remember this is the sum of the probabilities before and up to the value. So you can't just start at 0. We know it can be 0 right here, but we still have to show. So the first range will be if x is less than or equal to 0. Yeah, so that's show. So look, we here now, less than or equal to 0, we know is 0. So the capital F of x of it will be the integral from minus infinity to 0 of 0 dx, which is equal to 0. Redundant, but still put it. So that's the first range. So the second one, which is the important one, will be when x is less than or equal to 1, but more than or equal to 0. Yeah? So you're just looking at where the x could fall. So if the x fall in between here, anywhere in between here, the probability or the CDF will be 0. But if the x fall anywhere between 0 and 1, you need to know what the probability will be. And you could use just one equation, plug in your x value, and it will just give you what the probability is. That's the beauty of the CDF. Because by definition, it gives you the probability before and up to it, right? So here now, you just add up the probability. So capital F of x in this case, everything before, so it'll be, which is why I drew this line diagram. So now the x anywhere here, so right x. So between minus infinity and 0 is 0, plus, and then from 0 to x, in this case, number x could be anywhere in between here, but the range is just 0 to 1. So if the x anywhere in between 0 and 1, you have to integrate. So it'll be the integral from 0 to x, once it's in this range, of 1/3 dx. Right? So that's, when you integrate that, you'll get 1/3 x. You have x and 0, so b minus a, that's just going to end up being 1/3 x plus 0. Yeah, and that is the equation of a straight line. Y is equal to mx plus c. So you have a positive gradient and a y-intercept of 0. So between 0 and 1, your line will be 1/3 x. So you'll draw it up. Right, and if you wanted to know what it will end up, meaning like some of you trying to connect lines, just plug in where you end, where you're ending at. So in this case, you're ending at 1. So you can plug in 1 here. You'll just end up with the top piece being at 2. Yeah, so you just plug in 1. So you're not ending at 1. And that's the second range. And if I continue to move my x now, so y will be x in between 1 and 2. So that'll be a next range. So 3. So that is if x is less than or equal to 2 or more than or equal to 1. And that'll be capital F of x. So between minus infinity and 0, the area is 0. Plus, between 0 and 1 is at 2, flat out, can't pass it. I don't need to integrate that piece, because I know the max area I can get is at 2. And then if x in between 1 and 2, we're going to integrate between 1 and x, right? Because remember, x could be anywhere in between 1 and 2, right? So I'll be integrating 2/3. So we plus the integral from 1 to x of 2/3 dx. So going down here now, so continuing it. So it'll be 1/3 plus, we'll find this, so it'll be 2/3 x, and that'll be between x and 1. Yeah, and just continue the question. It'll be 1/3, and it's b minus a, so it'll be 2/3 x, and it'll be minus 2/3. Yeah, maybe let's bring everything together. Normal maths. So it'll be 2/3 x, and then 1/3 minus 2/3 is minus 1/3. So that will be the equation in between 1 and 2 for your CDF. So if you were to plug any x in between that range from 1 to 2, you will end up with the CDF, which is the probability that x is less than or equal to that value, straight up. Yeah, that is the beauty of it. So if you're sketching that the y-intercept is minus 1/2, so you know it kind of, it's a steeper. So if I want a y-intercept down here, we'll kind of have to get a little steeper. And so, yeah, a little steeper, right? But you understand the concept. I'll get steeper. Okay, I have a negative y-intercept. So yeah, that's connecting the lines. Alright, and then the last one, which is from 2 to anything above, yeah, don't really need to do anything, because the whole thing about probability, yeah, we're basically done here, because you already went from 1, you already did the range from 1 to 2, if x was to fall in between that range, which is here. So you did if x fall in between here, you can get the probability that x is less than or equal to that value. If x fall in between here, you get the probability that x is less than or equal to that value. But if it fall here, you'll see that it's adding up to something cool. So the fourth one, or those in green, if x is less than or equal to positive infinity, but more than or equal to 2 in this case. Yeah, because I went ended. Same thing, cumulatively add up the areas before slash the probabilities. So from minus infinity to 0, the area or the probability was 0, plus the area or the probability from 1 to 2, sorry, from 0 to 1, which is a third, and then plus the area from 1 to 2, which is 2/3, and then plus the area from 2 to any point from that 2 to positive infinity, which is 0. So that is what the state. And that's what we have in our line. If x was to fall anywhere in between here, the area you'll be integrating 0. So you just end up with 0. So 1/3 plus 2/3 is equal to 1. This here is how it does know you're correct. When you're doing this here, if you get anything but 1, you make a mistake somewhere. Which is why I love this method, because you could know innately if you make a mistake or not. Because you only have one way to get 1. So what this means in a probability standpoint is sum of the probabilities must add up to 1. Right? So in this graph that they gave us, so from here now, from 2 onwards, it will just be a flat line. So I'm going to draw it a little neater down. So the sum of probabilities must always add up to 1. It can be 1.2, 1.3, wherever it must add up to 1. So I'm going to sketch it a little neater so you can see what actually happened. So from 0 to 1, I'll end it here, it was this here, which was 1/3 x. Right, and then the other piece now, which was from 2, it got a little steeper. So you know this one ending at a 2. Okay, if you put the end point here, you get a 2. And the second piece, it ended at quite up here. Right, and this one here was 2/3 x minus 1 on 3. And if you plug 2 into this to get what the y value is, 2, so you get 4 on 3, 4 on 3 x. I'll do it here. So that is 4 on 3 minus 1 on 3, which is 3 on 3, which is 1. So it's supposed to end at 1. Okay, it's supposed to plateau at 1. Yeah, so anything here, the area is the sum of the probabilities before it will be 1. And this is the graph. There's your CDF here. So the y-axis is capital Fx. And that's it. That's your, there's 1. That's your CDF. So you just cumulatively adding up the areas, which is probability x, is less than or equal to any value x. So let me say, for example, let me see how practical this is. If Miss wanted to know what is the probability that x is less than or equal to 2.5, all I need to do is look on the graph. If the probability is less than or equal to 2.5 with 2.5 here is 1, the answer is 1. If I wanted the probability x is less than or equal to 1.4, first I have to find where I could find 1.4, which should be like right here, and then going up to here, but I don't know what that is, but I could just use the equation to get it. So if I was to just plug 1.4 into this, it will call for my answer, which is capital F of x. And you could rinse and repeat this graph, play with it if you wanted to. Another weird one you could do is the probability that x is less than or equal to 2 or more than or equal to 1. Some weird like that. So more than or equal to 1 but less than or equal to 2 will be this range here. So something cool you could do, you could actually just subtract this area here from 1 and you actually get the answer. Remember, this plateau is not 1. Yeah, and there are multiple ways you could use this graph. Because remember, it gives you the probability that x is less than or equal to any value once it's in the range. Right? That was that question. There wasn't anything. So I did the PDF already, which is just the flatline ones, and that was the CDF. The method, you use the line method. This is real, trust me. And you can actually use this to do any weird questions I'm going to give you to kind of see it on the graph, so you can have an idea so what the answer will be. So by all means, use it. All right, any questions? If no questions, I will going to continue. See less. So like continue to the other one. Okay, the next one. So let x be a continuous random variable PDF. Okay, no problem. Determine the value of key and sketch the PDF. The common f is PDF. So something remember is I remember you dealing with continuous random variables, right? So if I have a graph here and this graph ending here, now we see it ending at 5. The area, all this area here, if I was to actually integrate it, I'll get 1. Because the area under the curve is the probability. And the sum of the probability, which is equal to the sum of the area, are equal to 1. So you can actually use this to get anything you want. Because the sum of the probabilities is equal to the total area under the graph, which must equal to 1. You have to remember that. Because for continuous random variables, the probability is the area under the graph. Alright? So if I wanted to know what is the sum of the area, it would just be 1. You have to think about it. If you integrate the whole thing, you get 1. So for this question here, we could use that concept to get key. So if I integrate this, which is your PDF, between the bounds that I give you, which in this case is 0 and 1, I'm supposed to get 1. Yeah? Okay, that's usually normal calculations. So if I integrate this, so the k here pull out, you get x dx, so forget my dx, is equal to 1. So the integral of x is x squared on 2. So it'll be k x squared on 2. And you have to integrate that between 0 and 1, and it's equal to 1. So it's b minus a. So it'll be k on 2 subtract 0 is equal to 1. So k on 2 is equal to 1, and you carry 2 across. So k will equal to 2. And that was that. Nothing else. So even if we change up this question in any way, shape, or fashion, the concept is, as I repeat for the umpteenth time, if it integrate the total graph between, if she give you more piecewise functions, you can integrate that between the bounds. So if she has say kx is 0 to 1, kx is 1 to 2, you had to integrate the whole thing. And you just equal that integral to 1, and you can calculate for anything. The skill that you're testing here is if you know that the total area under the graph is 1, because the total probability is the total area, which are equal to 1. So that is what she's testing here, right? Alright, so the set sketch the CDF, right, which is the probability that x is less than or equal to x, which is just integrated. So the right here, the side, because I don't really have much piecewise functions for this one, shouldn't take up much space to do. So to get something cool, like I remember, that's kind of helped me. If you integrate common f of x, you will end up with capital F of x. Yeah, so if you differentiate, let me write this correctly. If you integrate f of x dx, you end up with capital F of x. So if you differentiate the PDF, yeah, it will, sorry, if you will end up with the PDF. So some cool I could remember. To me, that there was some cool I could eat. But anyway, so you're trying to integrate this. So we just did what the integral of it was kx squared on 2. So if I just plug back in k as 2, we just end up with x squared, right? So that's the integral of 2x squared on 2 dx, right? So it has put that in kx, sorry, I am right, 2x, sorry, not, yeah, 2x. So if you integrate this, you bring the 2 outside, and you just end up with the same thing we had before, 2x squared on 2, you just end up with x squared. Same thing I showed us. So you couldn't get that from here because you already integrated. So, but if you want to show the calculations, this is what it will be. You just integrate the PDF to get the CDF. Right, so I just use up the space I want to do the question, so I don't move it up. It's just gonna be a quadratic between 1 and 2. So as I said, it's not gonna take up much space. So between 0 and 1, just gonna be a quadratic. So that is it. Really how much to it they are to worry about. And if you wanted to know the upper bound of it, just plug in 1 into that. So it should end up with 2. Now minimize it. 1 squared is 1, yeah. So remember this is the CDF. So if I plug 1 into x squared, you get 1. Yeah, so this is your capital of x. Which is you get from integrating your PDF. So you integrate the PDF, you get the CDF, and if you want to do the upper bound of it, it'll be 1, and what has happened is from here it'll just plateau. Because anything more than the bound that I give you just have to be 1. It must always end at 1. Yeah, the top piece have to be 1 because the total area of the graph have to be 1. Yeah, that was that. And then part C now, the one the probability that x is less than or equal to 2, but more than a quarter. So what I will do is put a line and do the method I comfortable. So from minus infinity to 0, 0, and then from 0 to 1, it's 2x, and then from 1 to anything is basically 0. So I have that, and basically 1 is, or the set of 1s, is x had to be less than or equal to 2, but more than a quarter. Make sure that's what it said. Yeah. So where 2 is, 2 basically outside the bound that we want. So 2 here, so you here. And they basically want the area, so that'll be more than a quarter. So a quarter will be somewhere here. Yeah. So they want this. So basically they want the piece in green, which is this here. Right? But the cool thing is this 2 in a region where I know the area gonna be the total area or the probability gonna be 1. So if I was to just subtract this area here, we'll put it in a different color. If I was to just subtract this area here from 1, I will get the answer. Because remember 2, basically if you go back to the graph, plots with 2 quite here, which is 1. Yeah, so all you will do it is, we could say f of 2. I'm sure it here. So f of 2 is all of this. Remember, it's everything less than or equal to 2. So I'll write the definition. Subtract f of a quarter, which is everything up in orange. So everything in orange is well less than or equal to a quarter. And if you look at it, you end up with the piece that I want, which is the piece in yellow, which is this piece here. So the purple is everything less than or equal to 2, and the orange is everything less than or equal to a quarter. And if you subtract those two areas from each other, you get the yellow, which is what I want. So this will be f of 2, get that from the graph, is 1. Why? Because 2 here, go up, go across, is that 1. So we 1, subtract f of a quarter. If you had plugged this line alone, you'll have to integrate 2x and plug it in. But luckily we did that already because we have something called the CDF. So a quarter here, if I was to go up, I'll get this here. The equation of this line in the CDF is x squared. So I have to plug a quarter into x squared, and what I will give me is the area less than or equal to a quarter. So 1 minus a quarter squared, put that in my calculator. So 1 minus answer, oops, 0.25 squared. So you get 15 on 16. Yeah, that was that. Same idea. I love to use this because it helps a lot. If you want to, you could do this line and just plug in the CDF equations instead of the PDF equations. What I have here is the PDF equation, which is 2x. So you could just plug x squared. I will kind of make it easier so you could see all our work, because it just shows a linear relationship between everything. Instead of looking at the graph and trying to figure out what's going on. And that was that. That was calculate K, sketch, and a little bit of the question that she'd like to bring, which you use the CDF graph to get. Right? So anybody have any question on anything out of there before I move on to the other one? Can you explain the curve on the CDF graph? So when you say explain the curve on the CDF graph, what do you mean exactly? Because show you how I get the curve. You ask them how I get the curve or how I draw the curve. Which one? So you have to be a little more specific with it. How I get it? Okay, so you could use your mic, right? So I want to test if you understand it or not, which is okay. So you could talk on your mic, right? Your mic working? So you can help out everybody else. You don't have to use your chatting. Oh, okay, well, you let's say no, okay, I don't want to talk or mic not working. But anyway, so I'll follow the chat with you. So this common f of x here, this is your PDF, right? So if you want to get the CDF from a PDF, you have to integrate the PDF. But the problem is we don't know what K is. So you have to get K, which is what the first question was asking you to get. So the concept that we took advantage of is that the total area under the graph is the total probability, which have to equal to 1. So what we did, we integrate kx between the bounds that they gave us, which was 0 to 1, and this is equivalent to the total area under the graph. But we know the total area under the graph is equal to the total probability, which is 1. So we integrate this, so k is a constant, so normal integration, you pull out the k, x, dx, dx, let's erase this, and the integral of x is x squared and 2. So you end up with k and x squared on 2, right? And this here is still going to equal to 1. Yeah? So you're still going to continue the question like normal. So you have the bounds that integrated between, which was 0 to 1, and just like normal. So remember, it's b subtract a. So when you plug 1 into this, 1 squared is 1. So you're going to put k on, I'm going to check this, yeah. Yeah, small thing, that's follow. If you're confused, I would just stop. So you plug 1, k on 2, subtract 0, you get 1. Fling it 2 across, you get k as 2. So right now, this kx here is, now we know is 2x, which is good, as with the first piece. The CDF now, remember we had already integrated this. We kind of did it backwards to go forward, to go back again. So to get the CDF, you have to integrate the PDF. So which is this part I did here on this side. So when you integrate this here, you will end up with x squared on 2, but the 2's will cancel. Okay, if you look at this piece here, look at this piece here. This is what we get after we integrate. If you plug 2 into this, the 2's will cancel. So you're going to put x squared as the CDF. Yeah? So when you're sketching it, it's just x squared. Remember, x squared is a quadratic. When inside the quadratic starting from 0. So it will just be this piece here. So between 0 and 1, you have a quadratic. Yeah, and that's all x squares. And we know it ended at 1 because it's the CDF. Yeah. And one thing to remember, when you're supposed to end at 1, always supposed to end at 1. Right here, just go across. Because that's showing what the sum of the probabilities less than or equal to will be. So if I was at 3, you go up, there's 1, which makes sense. Because the sum of the probabilities less than or equal to 3 is 1. Because you're kind of out of the bounds of the graph itself. So that was that. So concept, concept, concept. You integrate any PDF to get a CDF. Yeah, total area, total probability is 1. Same concept you'll be using over and over. Alright, so you see what else we have. I think this is the script. Oh yeah, that was the 2 questions for continuous in the tutorial. So
Daniel,
gonna
one thing, right?
walk it through one time.
For the
Okay,
coup,
so
how we
now
know?
we gonna run through discrete random variables. This one, it tends to be the easy one, um, but it could be tricky according to how she brings it. Alright, I think I forgot one thing to show you. Oh, just show you it now. So the
Daniel, hello
area
again.
expectation
No.
of a continuous random variable. So kind of jumping the gun here, but also go through. So for discrete, if you understand discrete, you understand continuous. Because when you say that changes for continuous is that to get the probability, you have to get the area under the graph. So it's kind of the same concept that you're using to get the continuous. So the expectation or the average, which is mu, of a discrete random variable is just the sum of all x. Remember, discrete could only take fixed or discrete values using the definition to define it, of x by the probability x is equal to x. Right? It have no less than or anything, it's equal because discrete. And for variance of x is equal to e of x squared in the bracket subtract e of x all squared. And in terms of the one we used before, this here is the sum all x. Let's see something in the chat. Hey, so one question for the question, how you know is a curve and not a straight? Okay, which one? The CDF? How I know the CDF is a curve? As you're asking? Right, think about it. It's x squared. X squared is a linear or a quadratic. Simple question, but I will answer your question. Think about it. So the equation of a straight line is y is equal to mx plus c. So if I see anything 2x, 3x, 4x, 10x, I know it's a straight line. But the equation for a quadratic is ax squared plus bx plus c. So anything I see with a square in it, I know is not a straight line. So it have to be a curve. So that's how I know for sure. Yeah, I know for sure it's not a straight line. Can't be a straight line. If it was a ratchet, I would have never write a straight line. It's a sketch. It don't have to be exact. It's a sketch, right? So you know it's a curve. So you just draw a curve between the bounds I must give you, which is 0 and 1. And you know after 1 is plateau, and that is a sketch. So you don't have to worry about it. To make it simple for you, it don't matter what type of line you have, the two main types that you have to sketch, they are linear or quadratic, or curve if you want to call it that. Anything in the form y is equal to mx plus c is a straight line, straight line. Anything with the highest power being 2, or anything more than that which you will never ask you to sketch, is a curve. So you know, be kind of curve in nature. Right? Or minus if you want to call it that. If you had a minus here. So it wouldn't change too much. But linear and quadratic, same thing. She wouldn't bring anything more than that because others not intuitive enough to draw. Like you're not just going to draw something ax cubed. Nobody really does draw that. Anyway, so hope that, yeah, no problem, bro. Right, so x squared will be sum of all x of x squared by the probability x is equal to x minus, and this one here just the one before, but adjust over everything. So x is equal to x all squared. Yeah, and that's the two equations that you must memorize, and I will show you how to do this because you need to do the questions for discrete after. So you'll see how this real simple because discrete easier than continuous, right? But for continuous, it's the same understanding, same idea. The only thing that changes is the probability x is equal to x. That constraining because now for continuous, if you get values anyway, it could be anything less than, more than, it could be anything. It doesn't exist as at discrete points anymore. So same equation by editing it out. So the expectation of x, it will be the sum of all x. Well, so this part here is our problem, right? So it has no sum anymore for discrete. For continuous, sorry, because you integrate now. So you're gonna remove that. And you're gonna write x, because the same x as before. And now we're trying to get the probability. So you have to integrate to get the probability. Yeah, so we'll be integrating all x. And since they could give it as a piecewise function, it would just be, you just say common f of x dx. Okay, you're still integrating the PDF to get the CDF, right? So, and that'll be that's the same equation. So if they give you this piece here, all you will have to do is just run it through example. Actually, I could just use the example that this gave before, so that make it funny. So you can actually try it, but I just raw integration, honestly. Once you know how to use it. So for this question here, if I wanted to get the expectation of this, so all will be, alright, it's on top here. So the expectation of x will equal to, yeah, just kind of multiplying x by everything, right? So it'll be x by the integral from 0 to 1 of 1 to dx plus x by the integral from 1 to 2 2/3 dx. Alright, plus x by the integral from 2 to infinity of 0 dx, which makes no sense, but I just write it so you can see. So you're just adding up all those things, so you're integrating whatever and whatever. So you multiply this out, because remember this is x, right? So it's not a constant, so you have to multiply it out. So you'll be integrating 1/3 x, 2/3 x, and in this case, x by 0 is 0. So I'm going to remove that. before they get confused. So you're integrating these two, and whatever value you get afterwards, that is the answer. So that's to simplify it a little bit. Remove the x from here. They're going to go in here. Remove the x from here. It's going to go in here. And when you integrate this, I'm not going to do the full thing. So it'll be x on 3 between 1 and 0 plus, that'll be, this is wrong, because 1/3 x will be x squared on 6. And then this one here, it will be 2x squared, and then 2 by 3 is 6. Because remember, when you're integrating, you add 1 to the power and divide by the new power. So for this one here, I made a mistake. So it'll be x squared divided by the 1/3 by the 2. So the 3 by the 2 will give you a 6. So you have this one here, and this one here, and this one will be between 1 and 2. So you plug in like normal integration, b minus a, and you get your value. And that will be your expectation. So it's just x by the integral of f of x, which if it's a piecewise, it does have multiple pieces to do it for. And for the variance, assuming that you did the expectation already, because you need the expectation to do the variance, it has a piece in it. It will be the integral, so it will be x squared, integral, all x, f of x, dx, and then you have minus, and then you have basically this over again, which you're not going to write back. Yeah, it's just the same equation as before, x by the integral of f of x dx, which is the expectation. So the variance is the first piece is the x squared and then x, but it's the same thing as before. Same thing as you do that's no x squared integral 0 to 1 over 1/3 dx plus, which is this piece here, and plus x squared from 1 to 2 or 2/3 dx. Alright, and then after that you just subtract whatever you get for the expectation, all squared, and that is a variance. So that is the same concept as before. Right, so back down to the equations for it. So that is the expectation, and just like I showed you before, just look at the parallel for the variance. This is what we're trying to get, which is this. But the problem is you don't have this anymore. So you're just gonna add this also. You have no summations. So you're just gonna replace that with the integral of all x of common f of x dx. That's where that replace that. So this will be x squared integral all x f of x dx minus, and this piece here will just be x integral all x of common f of x dx, and that's all squared. And that's, so we just did continuous. It's the same idea. You have a piecewise function, so you have to do it for each x by each piecewise function in between the bounds that must give you. You get a flat answer. It's supposed to get a constant. Right? Okay, so any questions on these two equations? Because that's kind of the last thing I must wait to know. The expectation and the variance. How to calculate it. So any questions on those? Like any questions? It don't matter how simple it is. Make sure and memorize this. Because Miss will not give you this equation in the exam. You need to know it like the back of your hand. So make sure you remember it. Right, so if no question, I'll just continue to discrete. So as I explained, a discrete random variable, it can take fixed values. That is it. So they'll be labeled or displayed or presented to you in a different way as they are accustomed to seeing it. So let's tackle this one. Let's go to the last one. Here, this is the last one. Okay, now we'll tackle the last one. And you just work backwards. Think I'll copy and paste the same question. Okay, so you work on this one. Okay, that is easier to follow through. So probability density function PDF given for the discrete random variable in the table. So this is how you would give a discrete random variable. fixed values of x, as you see. Tab no 2.5, 1.2, 0.5, fixed values, discrete values. That's what they call it, discrete random variables. And at those specific x values, you have a probability. Yeah, so the norm we give it as the probability of x is equal to this specific x value and is zero otherwise. It don't exist in between. So with this, I'm going to go through the full thing, CDF, PDF, variance and expectation, and just that is it. Because it's the easiest one out of all of them, but it doesn't take any integration per se. So the first thing that we could plot is the PDF, which is kind of the easiest thing to do because it could only exist at discrete points. So the points that we have, just x here, you have 0, 1, 2, and 3. So at 0 is 1 and 8. At 1 is 3 and 8. At 2 is 3 and 8. And at 3 is 1 and 8. Yeah, and that's it. And just like before, the sum of the probability x is equal to x is equal to 1, which is the same as the integral of all x of common f of x dx, which is equal to 1. Total area is 1. Sum of each discrete probability is 1. Same concept. It's just for continuous, you're dealing with area. For discrete, you're dealing with like vertical dashes or spikes, if you want to call it that. They have nothing in between here. Zero. Nothing. Doesn't exist. So this is your PDF. So your CDF, you kind of could do that on the table. I should leave some room on the table. I shall use the table. Because I want to do my exam, let's use the table for everything. Okay, you could derive most stuff from the table. So let's extend the table down, come across, pow, 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 pow. So the notation for this is the probability that x is less than or equal to x. It's the same thing. Capital F of x is equal to the probability that x is less than or equal to x. This does not change. So same idea. So say we start at 0. The probability that x is less than or equal to x, so it'll be 1/8 plus 0, which we don't really know anything before it. And then at 1 is 3/8 plus 1/8, which is 4/8. And then at 2 is 3/8 plus 3/8, it's 1/8, which is 7/8. And at 3 is 1/8 plus 3/8 plus 3/8 plus 1/8, which is 8 and 8, which is 1. But must always stop or end at 1. So I say, all I can do is plot that. That's really all I can do. So it's be capital F of x. So you have your same bound 0, 1, 2, and 3. And between 0 and 1, I think Kivan asked me this. So this here, 1 and 8, 4 and 8, 7 and 8 and 1, these are equations of a line. Alright, so it is in the form y is equal to mx plus c, but it have no mx. It have no gradient, because the gradient is 0. So it just have a y-intercept. So if it was to visually predict how this going to look, a graph where the gradient is 0 is a horizontal line, because you just have the y-intercept. Because it would just be y is equal to c, which is just a line that cuts the y-axis. That is type all the time. To have no gradients, horizontal line. Yeah? So all it's gonna be 1 and 8 between 0 and 1. Pow! 1 and 8. So you know it's not gonna be a curve or anything. That's 1 and 8 flat. And then between 1 and 2, the set is 0 and 1, so between 1 and 2 is the other one. Right? So everything less than equal to 2. 4 and 8. And 4 and 8. And then the other one is 7 and 8, which is up here. And the other one is 1, which I don't have enough space for. And that's it. Steps. Alright, so Larry, that is it, you know. So that's basically it for the CDF of the graph. So everything less than equal to 0 is 1 and 8. You keep going and going and going and going. Okay, so where we at now? Alright, so the next thing we have to get is the expectation of x, which is the sum for all x by the probability x is equal to x. So as I said, you could just use the table to continue the working, but since I already use the table, I had to create my own table, or you could kind of do it in your head, but I hate doing that. So you have x is 0, so you have to square that. So we do it piece by piece. So 0 squared is 0, leave some space, plus 1 squared is 1, leave some space, 2 squared is 4, leave some space, 3 squared is 9, leave some space. You could do this in a table and continue, but I didn't leave space. So the next piece, you have to multiply by each respective probability, which in this case, the 0 will be 1 and 8, the 1 will be 3 and 8, the 4, which is a 2 squared, will be 3 and 8, and the 9, which was the 3 squared, which is 1 and 8. Kind of like adding up all those to the 0, the 3 and 8. This here is 12 on 8, because 4 by 3 is 12, and this here is 9 on 8. So 12 plus 9 is 21, 21 plus 3 is 24, and 24 divided by 8 is 3, I believe. So there's the expectation. And then, yeah, variance, same idea, now we're doing the, just now, make a big mistake, but then realize it's x, not x squared. No, I was doing x squared. I mean, what I did there is the first part of the variance, so I need the answer for it. But I'll keep that aside. Make a mistake. Remember, it's x by the probability x is equal to x. So there will just be 0 here. This here is just 1. This is just 2. And this is just 3. So let's be careful. It's not x squared, it's just x. So everything here will change. So this will be 3 on 8 still. This will be 6 on 8. So 3 on 8, 6 on 8. This here will change to 3 on 8. And the answer will change. And so you have to be careful with it because the x by the probability x is equal to x. So 0 by 1 on 8 is 0, 1 by 3 on 8 is 3 on 8, 2 by 3 on 8 is 6 on 8, and then 3 on 8 by 1 on 8 again will be 3 on 8. So you add up this now. So 6 plus 3 is 9, 9 plus 3, 9 times 12 on 8. Yes, so that makes more sense. One math, so do this. So there's the answer here. Because with respect to the equation, that is what I'm supposed to do. Now, which is what we're supposed to do then, is equal x squared by the probability x is equal to x. Subtract the sum for all x of x, which is the expectation, all squared. Alright, so basically what I'll do for before was what I was supposed to do for this piece here. So I had to do 2 which we catch it. So x squared was 0, then 1 squared is 1, then 2 squares 4, then 3 squared was 9, and then multiplied by the respective probability. So same here as before, but I did it in the wrong place. So let's just to make sure 1 and 8, 3 and 8, 3 and 8, 1 and 8. So I think I already had the answer for it, so it was 24 and 8, which is 3. Because we did it already, we just did it in the wrong place. So to bring everything together, we already have the answer for this. So the variance would just be a 3 and then subtract. So I could probably do that. 24 and 8 subtract. And this here is what this was. It was 11 and 12 and 8, which is what? 2.25. So this is just 3 subtract 2.25, which is 0.75. And that's the variance. So that's a recap. We got a big mistake in the first piece. The expectation is x by the probability x is equal to x. So we have the x's already, which is the variables that I gave you, and then multiplying it by these here, and then just adding them up together. That will give you expectation. And then for the variance now, it's the same idea, but instead of using x, we have how to get x squared, and you just use the same process. X squared by the probability x is equal to x, and you add all of them together. And that will give you the first piece of the variance, and you just subtract the expectation squared, and that will give you a variance. So that is what this equation here means. Yeah? So that's basically discrete. So CDF, PDF, mean, variance. So I have no tricks to it really. Alright? So I tried this one. Right, before I continue, any questions on this? I don't want to confuse anybody. Right, okay, so hopefully I recover quick enough. So this one here is a little more involved, but the same idea. So instead of giving you the PDF, here they give you the CDF. Because capital F of X is your CDF, right? So what they give you, capital F of X is the probability that X is less than or equal to X. So you have to remember this. Have to, because this is basically the foundation for CDF for most other questions. So looking at this table, this means that the probability that X is less than or equal to 1 is this. Less than or equal to 2 is that, 3 is that, 4 is that, 5 is this. So I'm sure there's something cool, right? So you could actually use this to extrapolate these things. So basically what I want you to do is I want you to get the PDF. So I don't know if you'll remember, if you integrate the PDF, you get the capital F of X. So you could use this more for continuous. You can't really have integration for discrete. So we have 0, 1, 2, 3, 4, and 5. And we're looking for the spikes, which is the individual probability at that point. Yeah, but we don't know because they gave us the CDF. So if I wanted to write it out, f of 1 would be the probability that x is less than or equal to 1, which in this case is 0.05. Yeah, so what this means really, without writing this, come on, you're working in discrete. This is the probability of 0 plus the probability of 1, and this discrete. I have no value for every single thing in between. So that is this here. Capital F2 is P0 plus P1 plus P2. Keep going. F of 3 is P0 plus P1 plus P2 plus the probability of 3. And capital F of 4, P0 P1, P2, P3, and then you have the probability of 4. And the last one, which is capital alphabet, 5 is 0, 1, then you have 2, 3, 4, and last one is 5. So if I wanted to get what the probability or probability x is equal to 5 alone, looking at these, where you have to do, you're trying to look for something that looking like f of something, subtract f of something, will give you the probability x is equal to something. That's really the concept, but what you have to see the pattern. So when you're subtracting, what happens is you're kind of carving out space. Some stuff will cancel, and the thing that remains will be the answer. So if I was to subtract f of 4 from f of 5, this will cancel with this. Pow, 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 and I'll just end up with the probability of 5 alone. So what I did, f of 5 subtract f of 4 is the probability x is equal to 5. So let me see if the pattern will still hold for everything else. So if I wanted f of 4, using the same pattern, it will be f, so this was our probability x is equal to 5. So if I wanted the probability x is equal to 4, using the same pattern, it will be f of capital F of 4 subtract capital F of 3. So let's see if it still makes sense here. So if I subtracted f of 3 from f of 4, so this will cancel with that. Remember, these should be the limit here. This will cancel with this with this, with this, and it just end up with P4, which is where you want alone. So this here will give you the probability x is equal to 4. So we use the same pattern. So if I wanted 3, it will be f of 3 subtract f of 2. We see if that makes sense. So if I subtract f of 2 from f of 3, this will cancel with that, this will cancel with this, P2 will cancel with P2, and I would have end up with P3 alone. Now, to continue the same pattern, x is equal to 2. It will be f of 2 subtract f of 1. So if I subtract 1 from 2, so P0 will cancel with P0, P1 will cancel with P1, I would just end up with P2 alone. And continue straight out. So last one, so this will be f of 1 subtract f of 0. This will give you the probability x is equal to 1. So in our case, it have no f of 0, capital F of 0, which so that means the probability is 0. So basically, capital F of 1, probability x is equal to 1 is literally just where you have as the probability x is less than or equal to 1, which is this here. So it have no capital F of 0. So let's just go and turn into capital F of 1 subtract 0, because it have nothing fit. Which will just end up being capital F of 1, which is, yeah, sorry. Analyze it. So if you wanted to sketch it, so that we actually get the values. I'll use my so for the first one, I want to get 5. So it's f of 5 subtract f of 4, which is 0.25. And then for 4, it's f of 4 subtract f of 3, which is 0.15. And for 3 is f of 3 subtract f of 2. And f of 2 is f of 2 subtract f of 1. And then f of 1 is f of 1 subtract f of 0. And that is it. That's all. So it's just, if you want to look at the table, it's just this subtract this. That will give you, if you subtract 1 from 2, you get 2. Because of this, I'll show you here. You kind of see what will cancel out with each other and remain. Because you want P5 to remain, which is the probability x is equal to 5. And that was that. So all this chalala did here was to show you. Alright, so any questions on that? No questions. Okay, cool. Nice. So that was kind of the end of it. This question here, the concept, you can use it for the first one, which was this. So I'll just run through this. So for the first one, you could get P3. Okay, if you subtract 2 from 3, you could get this. So it'll be 0.67 subtract 0.32. So it'll be 0.35. And then this is the probability x is more than or equal to 2 and less than or equal to 4. So remember this already in the CDF form. You gotta remember that. So since already in the CDF form, f of 4 is everything here. Any other. That everything less than or equal to 4. Everything less than or equal to 2 would be this. So if I wanted the answer should be the piece that remaining, which is the piece in green. Yeah, but small problem. So this here, everything less than 4 is 0.9, and everything less than or equal to 2 is 0.32. So if you subtract those two, you should get the answer. So it'll be capital F of 4, subtract capital F of 2. So everything less than 4, subtract everything less than 2. So this will be 0.9 subtract 0.32. And I get 0.58. Yeah, and the last one, the probability x is more than 1. So, sorry, more than 2. I have no idea why I see 1. So 2, everything more than 2 will be this here. Come on, but they say more than 2, not more than or equal to. So that'll be everything here. Yeah, so you can rewrite this in an easier way. Because everything more than 2 is inadvertently the probability x is less than or equal to 2. Yeah, if you look at it properly. Because more than 2, it starts at 3. So if I want to know this, I could just carve this out. Because it's the same thing. Yeah, so since I said more than, it would just be 1 subtract this. Because you carve it out already. So you're just subtracting the piece I got shaded in red. So you're subtracting this piece from the total. And we know the total probability is 1. So this here will just end up being 1 subtract the probability x is less than or equal to 2. Because you carve out this piece. So that will be 1 subtract. Everything less than or equal to 2 is 0.32. Because this is CDF. 1 subtract 0.32. And that is 0.68. And that was it. That was that. Right? So that was it. That was discrete and continuous. So that is basically everything you need to know about it. So before I continue, any questions? It doesn't really matter where to make sure that I understand everything here. So no questions. No problem. Nice. So that was the end of that. So I went through everything. So I did discrete continuous CDF, PDF, expectation, and variance. make sure and do the questions and practice it. Once you understand the concept, you could apply it to any question. All we're going to do is just change up the values or add more piecewise pieces to the graph, which is the same idea. Just how to do a little more integration to it. So that we jump into the distributions. I will see how much I could get done, but I've already started and I could always just you have the solutions to it and you once you understand it, you could always do it. So I run into this and you bust out after. So with the distributions for discrete and continuous, we have something called special distributions for both discrete and continuous. We call it special because it's special. It's not as straightforward as what you did before. So the ones that Miss want you all to know under discrete, you have binomial, you have Poisson, uniform, and exponential. Exponential is a weird one. I think it has a question. Exponential. So those are the ones that I just want you all to know for discrete, and for continuous, the only one that you wait to know is normal. Normal or Gaussian distribution. I do not spell Gaussian, but normal is the popular word for the normal distribution. Right? So these are the two. What I'm going to do in this session, I want to show you how to know what distribution to use. Because once you know what distribution to use, using the distribution is just plugging values into the equation. It's nothing difficult about it. The hardest part is knowing what distribution to use based on how the word the question. Because if you can know what distribution you're using based on how the word the question, and you already memorize the equations for the distribution, which everybody should know. What will separate the sheep from the goat is those that actually know what to use when. Alright, so let me start. So minus all the equations and stuff, which I will write, but let me go through it. So the first one is something called the binomial distribution. Remember, these are for discrete random variables. So when you use a distribution, you must state the random variable in the question, which is x. X is always denoted as the random variable. They will always tell you what the random variable is in the question. Is it thing they're manipulating or looking for? So you write it as x follows a binomial, or bin for short, and the parameters for a binomial are n and p. So what that means is how you will know when to use a binomial. You're doing something a certain amount of times and you want to know what is the probability of succeeding n amount of times. So you're doing some over and over, over and over. So they could say you write the exam 20 times. And they want to know what is the probability that you pass 7 times. So you see how to word that question? So to know when to use the binomial distribution is n successes, or it could be failures. Why? Because it's determined by what you deem as the random variable. But what separates it is n successes or failures in n tries. Change it from n to x. Yeah, so x successes or failures in n trials. So you're doing something over and over and over and over and over, and you're checking to see where's the probability again of success. Simple thing, you go Galactica, them games, whatever it is. So you can play that game a fixed amount of times, and you want to see what's the probability of you actually winning the game. 3 times, 5 times, 10 times. So how I word that, it has to be a binomial because it falls under the stricter definition of x successes or failures in n trials. And p is just the probability of a success. And that has to be the same for each trial. It can't change. And by default, Q is the probability of a failure. And the sum of the probabilities had to add up to 1, so P plus Q must be 1. That will hold no matter what type of probability you're doing. So sum of successes or failures in n trials. You're doing something a certain amount of times, and you want to know what's the probability of you succeeding or failing 10 times, 3 times, 4 times, 5 times, etc., etc. So the equations for them, so the probability x is equal to x, which means the probability of you succeeding x amount of times is nx, which is the combination, which you can do in a calculator, of p, which is the probability of success, to x by q to n minus x. Right, so you can do this in a calculator. So if you actually look at a calculator, if you have a Casio, you see NPR or NCR, you could actually just use that to get this first piece here. So you can probably try it. So like if I wanted 3, 6, this would be 3 C 6, so it would be 3 shift NCR 6. Oh, the way around, and you get answer. Right, so there's the same idea. Obviously, 3 and 6 not really gonna make any sense. Well, okay, you can't have n trials and 6 successes. So you try the other way around. So it'll be 6 and 3. Yeah, so 6 number of trials, 3 successes. So that'll give you 20. So you can actually put this in a calculator to get the answer because you have a combination function in your calculator. And well, P is your probability of success, X is the amount of successes you want, Q is the failure, and N is your number of trials. That's one equation, just comes together. Once you know what each variable is, just, as I say, plug and play. Alright, and then it's discrete, so plotting the PDF is the same. Right, so you do 1, 2, 3, 4, whatever, and you get the probability and you plot the PDF, and the same steps for your CDF. Probability less than or equal to x is the same with the discrete. So the 2 expectation is NP, and the variance is NPQ. But binomial, you use it when the number of successes and failures you want in a certain amount of trials. As when you will use the binomial distribution to get answer or probability. Right? So the other one is something called the uniform distribution. So the random variable x follows a uniform distribution of p. So the thing about uniform distribution or the rectangle distribution, the probability of every single outcome is the same. It's literally rectangular. So if you have to plot the PDF of it, it would just look like a rectangle in between B and E. Yeah, some of the probabilities is basically the same, it's still 1. Alright, but the area underneath this is still 1. It's something like continuous, but it's not continuous. It's a rectangle. So if you wanted to do line by breadth, you'll actually realize that there's 1 for the area. But the thing about it for this, for uniform distributions, the probability of any value is same. Example of this is rolling a dice. No matter if you roll a dice 1, 2, 3, 4, 5, or 6, the probability of getting any of those values is still 1 on 6. It doesn't change. This is a uniform distribution. Everything had the same probability of occurring, no matter what it is. So that's why that always look like a rectangle. They're just flat because the probabilities are the same. Alright, so this one is uniform. Why? The probability of each occurrence is the same. That is equal to that. And they call it the rec function. And well, P is basically the same. So they always give you what P is. And the other one, our next popular one, Poisson distribution. So this one, so X follows a Poisson distribution PO a lambda. So what lambda is, and which is the definition for Poisson, is the mean number of occurrences in an interval of time or space. Or space, yeah. Space meaning like a production line, the amount of failures in 5 products or something like that. That would be by space, and obviously time is time. So this is basically how you just think about it. So they will give you a question and they will say, where's the probability of 3 failures in 10 trials? But it have to be a specific time that will always give you the specific time. This is not trials, right? It's just you looking at something or you doing something and you're given your time in it for a stopwatch. And then you're waiting and you check to see where's the average amount in that specific time. Or you're looking at a production line for every 50 products that pass, what is the probability of it being defective? But that is specific to that interval of space in that case. Or if you time it, there's the time interval. Alright? So lambda is your mean number of occurrences in that specific time frame or space. So this is discrete. So the equation for your PDF is lambda x by e to the minus lambda by x under x factorial. So x factorial, if you remember from pure maths, so 2 factorial is 2 by 1. 3 factorial is 3 by 2 by 1. 4 factorial is 4 by 3 by 2 by 1. And the cool thing is, you could just do it in your calculator. So you could actually do factorials in your calculator. Some people don't have the function, but I think everybody should have the function. So you have to investigate how to do a factorial in your calculator. But for me, it have a symbol that looks like an x factorial in your calculator. For me, it's on top of x to the minus 1. For you, it might be different. So if I want to know what 6 factorial will be 6, shift, press that button, and it will give you the answer. So 6 factorial is 720. So investigate that. You should have a function in a calculator that you could do factorials. Right? And the last, that was the last one for the discrete. That must will wanted to know. And the cool thing about this one here is the variance is equal to your mean, which is equal to lambda, which is the cool thing. So if Mr. ever asks you what the mean or the variance of a Poisson distribution, it would just be lambda, which is your parameter. So it's kind of the easiest one. And the last one is just the normal distribution. That's just continuous. So continuous, it follows a bell curve, which should be familiar, but if not, that's how the probabilities will look when you do an normal distribution. And the parameters, you have your mean and your variance. So your mean is just the central piece, and your variance is the separation, how it's spread. You can see the spread, that's a better way to see it. And there's a PDF And the equation I just wanted to know for this, which you have to use for a lot of other proofs. Like this. So the 1 on the square root of 2 pi sigma. The square this will only over that by e to the minus x minus mu squared all on 2 sigma the root 2. Right? So that's what you need to know for this here. Your CDF for this is a little different. Remember, to get the probability is the area under this. So that's really ask you to get that. But for now, pause on that. So I'll pause there with the distributions. I will run through the exercise, which is the tutorial, in terms of what distribution to use because of time, and then we'll continue. So somebody could just send me a message in terms of when the midterm is for probability, so I'll make sure I'm covered. But you all should be able to do it. So later on, should just click on button. So you'll notice that the word and of it is similar. So a binary source generate digits 1 and 0 randomly with probability 0.6 and 0.4. So they get the probability of success or failure depending on what your random variable is. So they said what is the probability that you get 2 1s and 3 zeros and a 5-digit sequence. So basically they're sending out 5 and checking to see if 2 of them is what you want or 3 of them is what you want. So this would be a binomial. Because we say one the amount of successes or failures in n trials. Yeah, so you could use your binomial for this. So this would be, you could choose anyone to be P or Q, you'll get the same answer. So in this case, you can say this is P or Q. And the 2 for the 1, if you say you want the success to begin at 1, this would be x. And just work it like that. So it will be n is 5, your success in this case is 2, p in this case is 0.6 to the x, which in this case is 2, and we have 0.4, and n minus x, so n is 5, 3, so it will be 3. And you just apply the calculator and you get your answer for this. And this one here is the same idea. We can try. 16, look how they word this one. So you can kind of see how it differs and how she does word it. So the cell and noisy transmission channel has a per bit error. So they give you a P of this. So it calculate the probability of more than one error in 10 received digits. So they want the probability of getting a success in n trials. It's the same definition that we'll be going through. If you're thinking it's sounding familiar to Poisson, you will see when you do 17 how it is different, how it is worded, because it never gave anything in time or space here. So it can't be Poisson. You will see when you read 17 how it is different. So this here will be a straight binomial. And in this case is 10, and x is 1 here. So when you set in the top, n is 10, the 1 to 1. P is 0.01, x is 1, and if P is 0.01, Q had to be 0.99, and n minus 1 is 9. Yeah, and when you put in a calculator, you'll end up with, but they said in this case, the probability of more than one error. So if this is 1, so more than 1, you can just say 1 minus. 1 minus, this should give you everything more than 1. Yeah, so this is the probability. So 1 minus the probability x is equal to 1. We'll give you everything else that you need. Okay, this tree. Right, look at 17. So the steady number of telephone calls arriving at a switchboard during any 10-minute period. So they gave you a specified time for it to happen. And it is known to be, well, in this case they gave you it, but even if it didn't give you it, you will know it's Poisson because it gave you the period, time period, specified time or space, time. So this here is a straight up Poisson. And look at how they ask in the question. Find the probability that more than 3 calls would arrive in a 10-minute period. So the difference between how the Poisson is worded this here have nothing to do with you plugging this into the equation. Compared to the ones before, this 5 important because that 5 is the amount of trials. This 10 here is important to the question because you're using that in the question. But for Poisson, this is just the time frame they give it here. That really have nothing to do with you plugging in 10. So this here is just Poisson. So they said more than 3 calls. So you could just do 1 minus probability x, said more than 3 calls. So it'll be less than or equal to 3. And that will give you the answer. Right? 18, this was the one. They gave you the exponential one. Now this one here is exponential also. So exponential is like Poisson, but in this case they're changing the interval of time and space. Alright, 21 and 22 is the normal distribution questions. Right, so sorry that time ran out, but we did 11, we did 12, so those done. 15 you could do because you already have the equations fit. Remember is n successes in n trials, or x successes in n trials. This one here is binomial. Look at how the word is Poisson. They must give you a specified time or space. And then 18 is exponential. Let me just give you all the exponential quick. I don't think I wrote it down here. And we could bust it. So exponential. I'll send you all this document when I finish with it. Without any notes. What? So the x follows the exponential distribution. And the parameter is lambda, so it's like the Poisson. Right, so the PDF is lambda e to the minus lambda x. Just like before, as I said, there's a plug and play. So there's a PDF and some important stuff. So your mu is 1 on lambda, and a variance is 1 on lambda squared. Right, and the last two things in terms of getting the probabilities, which is your CDF, the probability that x is less than or equal to a is 1 minus e to the minus a lambda, and then other one is the probability that x is more than a is just e to the minus lambda e. Right, so with that said, that is all the distributions that end the tutorial. So what you all could do is attempt the question and just send my picture, and I will correct it for you and let you know if you do that correct or other than that, that is it for class. Alright, so any questions?